Calculation instruction. Introduction to calculation instructions. This section of the course mainly explains the programming calculation instruction of the JAKA app. It contains the following parts. 1. Calculator instruction. 2. Mathematical function calculation instruction. 3. Comparison and logic operation instruction. 4. Plan transformation related instructions. 5. Direct and inverse solution instructions. This lesson lasts about 20 minutes and the course objectives are 1. Proficiency in mathematical calculations and logical calculation instructions. 2. Briefly understand the related instruction of the plan transformation. First, look at the calculation operator instructions. Click the drop-down list in the middle of the calculation operator to select addition, subtraction, multiplication, and division operation. Let's look at an example of the application of the calculator. First, open the socket connection. Set the program variable a, b to 3 and 2 respectively. And then use the socket to send two variables to add, subtract, multiply, and divide to obtain a result of exponentiation. The following figures show the network debugging assistant server receiving results. The second is the mathematical function calculation instruction. Click the drop-down list of the instruction to select the corresponding mathematical function. Look at the example on the right. By sending the calculation result of the math function, the function can be cosinus, sinus, tangent, arcsinus, arccosinus, arctangent, natural exponent, natural logarithm, rounding up, rounding down, absolute value, square root. The following figures show the result of the function calculation received by the socket communication. Comparison operators. Click the drop-down list of the comparison operators. You can select less than, greater than, equal to, not equal to. Then less than or equal to, greater than or equal to, and the instruction returns the logical true when the conditions are met. Logical operators like AND operation means like both are true and the result is true. Logical OR operator if one of the two is true. XOR operation, the result is true when the two are different. Logical negation operator, the result is true when the condition is false. Logic operations can be nested. Position addition command. Position variable or teaching point can be dragged in, and the command return value is a calculation result. Look at the program example on the right. First, open the socket communication. The socket sends the result of the position calculation. Moves linearly to the position variable P1, and then makes a relative linear movement under the user coordinate system. The moving parameter is the unknown variable P2. After the movement is completed, the socket sends the current flange center of the robot position coordinates. Then, move linearly to point P1 and move linearly to the calculated result. The socket sends the position of the flange center again. The following figures show the result of the socket 3 times. We will see that the results of the socket 3 times are the same. The understanding of the position addition command is shown in the figure on the right. P1 is the Cartesian coordinate of the tool in a user coordinate system. P2 is the position to be added, and the parameters are 6/10. Its function is to first move P1 around the user coordinate system X, Y, Z, shift 10 mm in each direction, and then rotate P1 around the positive x-axis of the user coordinate by 10 degrees. Then rotate P1 around the positive direction of the y-axis in the user coordinate system by 10 degrees. Finally, turn P1 around the z-axis in the user coordinate system by 10 degrees. The relative linear motion in the user coordinate system is a function, and the transformed pose is the result of the position addition. Position subtraction instruction. Drag in a position variable or teaching point. The return value of the instruction is the calculation result. Position is calculated in Cartesian coordinates. Look at the example on the right. Open the socket connection. The socket sends the result of the position subtraction. The robot is applied to the point P1 in a straight line. Under the user coordinate system, the relative linear motion Rz is minus 10 degrees. The relative linear motion Ly is minus 10 degrees. And the relative linear motion is Rx minus 10 degrees. Relative linear motion x, y, z each translates minus 10 millimeters. After the movement is in place, the socket sends the position coordinates of the robot's flange and center, which is applied to the point P1 in a straight line. The linear movement is the result of the position subtraction. The socket sends the position coordinates of the center of the robot flange. And we will see that the result of the three socket sendings are also the same. The understanding of the position subtraction command is shown in the figure on the right. P1 is the Cartesian coordinate of the tool in the user coordinate system. P2 is the position to be subtracted, and the value is 6/10. Its function is to first rotate P1 around the z-axis of the user coordinate system by minus 10 degrees, then rotate P1 around the user's y-axis by 10 degrees, and then rotate P1 around the user coordinate system x by minus 10 degrees. Finally, P1 is shifted by minus 10 millimeters along the direction of the user coordinate system x, y, z. And its change in order is just the opposite of the order position addition. The changed pose is the result of the position subtraction. Position change instruction. You can drag in position variable or teaching point. The return value of the instruction is the calculation result, and the position calculation is Cartesian coordinate. Look at the example on the right. First, open the socket communication. It sends the result of the position transformation. The robot moves linearly to the position of the variable P1. Then the robot makes a relative linear motion under the tool coordinate system. The motion parameter is P2. After the robot moves in place, the socket sends the coordinates of the center position of the flange, and the robot moves linearly to the position of variable P1. The robot moves linearly to the result of the position transformation. After the robot moves in place, the socket sends the coordinates of the center position of the end flange of the robot. Here, we can see that the socket received the three same results. P1 is the Cartesian coordinate of the tool in the user coordinate system. P2 is the 6 parameters to be transformed. Its function is to first translate P1 around the tool coordinate system direction x, y, z by 10 millimeters. Then rotate PE around the z-axis of the tool coordinate system by 10 degrees. Then rotate P1 around the y-axis of the tool coordinate system by 10 degrees. P1 is the Cartesian coordinate of the tool in the user coordinate system, and P2 is the 6 parameters to be transformed. Its function is to first translate P1 around the tool coordinate system direction x, y, z by 10 millimeters. Then rotate P1 around the z-axis of the tool coordinate system by 10 degrees. Then rotate P1 around the y-axis of the tool coordinate by 10 degrees. Finally, P1 rotates 10 degrees around the x-axis of the tool coordinate system, and the change position is the result of the position transformation. It is equivalent to the relative linear movement under the tool as we advance. Let's look at the comparison of two functions. One is the position transformation instruction and the other is the position addition instruction. Both of these instructions return a Cartesian coordinate of the position in the user coordinate system. Two physical meanings. The position transformation is equivalent to the target point in the tool coordinate system. The dynamic coordinate system rotation sequence is Z, Y, X, and the translation rotation transformation is performed. The position addition target point is below the user coordinate system, and the static coordinate system rotation sequence is X, Y, Z. The rotation transformation is equivalent to a relative linear movement under the tool coordinate system, and the position addition is equivalent to a relative linear movement under the user coordinate system. Position calculation and inverse transformation. The usage is to drag in position variables or teaching points, and the return value of the instruction is the calculation result. See example on the right. Set the user coordinate system to open the socket communication, and it will send the result of the P2 position inverse transformation. And the robot moves straight to P0. The robot moves in the relative linear motion under the tool coordinate system, respectively rotates negative 10 degrees around X, then rotates negative 10 degrees around the Y axis, then rotates negative 10 degrees around the Z axis, and finally translate a negative 10 millimeters in each X, Y, Z directions. After the robot moved in place, the socket sends the coordinates of the center position of the end flange, and the robot moves to the result position of the inverse transformation of variable P2 in a linear motion. After the movement is in place, the socket sends the coordinate of center position of the flange of the robot. Have a look. The data received by the TCP assistant server 3 times is the same. An understanding of the inverse transformation instructions is as shown in the example on the right. P2 is the Cartesian coordinate of the tool in the user coordinate system. Its coordinates are 6 tens, P0 is the 0 position, its coordinates are 6 zeros. And its function is to first move P0 around the tool coordinate series, rotate the x-axis by -10 degrees, then rotate P0 around the y-axis of the tool coordinate system by -10 degrees. Then rotate P0 around the z-axis of the tool coordinate system by -10 degrees, and finally move P0 along the x, y, z of the tool coordinate system. When the direction is shifted by -10 millimeters, the posture after the change is the result of the inverse change, and the changed order is the opposite of the changing position. Calculate position distance command. Look at the example on the right to open the socket connection. It will send the result of calculating the position distance P1, P2, and send the sum of the squares of the x, y, z difference between the two positions P1 and P2. And then open the result of the root sign. The result received in the socket is 173.205. The result received is twice the same. Calculate position distance command understanding. Return position variable P1 and P2 position parameter x, y, z difference of the square sum, and then open the root sign, that is the distance between P1 and P2 in the space position. Calculation instruction. Interpolation point. See the example on the right. Set the program variable count to 1. Open the socket connection loop 5 times. The starting position of the palette movement is 1, and the palette movement is one-dimensional and has 5 points in total. The 2 points of the pallet are respectively P1 and P2. After the pallet is in place, the center position of the flange at the front end of the socket sends the coordinates. The robot moves to the position of the interpolation point P1, P2 in a straight line. After the movement is in place, the socket sends the coordinates of the center position of the end flange. After the movement is completed, the count variable is increased by 1 and the cycle moves 5 times. The following figure shows a result of 5 pallet movements and 5 interpolation point calculations. Understanding of the interpolation point instruction. Calculate the position of P1 and P2, that is the poster accordingly to the proportional difference. Refer to the pallet instruction. The pallet in the right picture is a one-dimensional pallet with a total of 5 points. The 2 points of the pallet are P1 and P2. The position of the pallet movement is consistent with the result of the position calculated by the interpolation point. Plane transformation instruction. X, Y plane transformation. See the example on the right. Open the second connection. It will send the plane transformation result. The robot moves in a straight line to the P1 position coordinate. The robot moves in a relatively straight line under the user coordinate system. The parameters are X, Y, RZ respectively 10. After the movement is in place, the socket sends the end of the robot coordinates. The robot moves linearly to the result position of the plane transformation. After the movement is in place, the socket sends the coordinates of the center flange position of the robot's end. We can see that the result of the 3 receptions are the same. The understanding of the plane transformation command is as shown on the example on the right. P1 is the Cartesian coordinate of the tool in the user coordinate system. Its function is to first translate P1 along the user coordinate system, X, Y directly by 10 mm, and then move P1 around the user coordinate system. The Z-axis rotates 10 degrees and the change position is the result of the plane transformation. Plane transformation YZ can be used to drag in position variable or teaching points. And the command returns value is the calculation result. In the example on the right, the socket connection is opened. The socket sends the plane transformation result. The robot moves linearly to the position P1. And then it moves in a relative linear motion under the user coordinate system. The parameters are Y, Z and R axis respectively, and the socket sends the end of the robot after the movement is in place. The coordinates of the center flange position, the robot moves linearly to the result position after the plane transformation. Then the socket sends the robot end flange center position after the movement is in place. The following picture shows the socket received in a result. We will see that the data received 3 times is the same. An understanding of the plane transformation command, as shown in the example on the right, P1 is the Cartesian coordinate of the tool in a user coordinate system. Its function is to first translate P1 by 10 mm along the YZ direction of the user coordinate system, and then move P1 around the X-axis of the user coordinate system, rotate 10 degrees, and the change position is the result of the plane transformation. Plane transformation ZX. See the example on the right. The socket sends the result of the plane transformation. The robot moves linearly to the P1 position and the robot is below the user coordinate. Make a relative linear motion. The parameters are Z, X, Ly, 10 each. After the motion is in place, the socket sends the coordinate of the center position of the end flange of the robot. Then the robot moves in a linear motion to the result position of the plane transformation. After the robot is in place, the socket sends the coordinates of the center position of the flange. The following figures show a result received by the socket. We can see that the result is the same 3 times. The interpolation of a plane change destination is shown in an example on the right. P1 is the Cartesian coordinate of the tool in user coordinates. Its function is to translate P1 along the X and Z direction of the user coordinate system by 10 mm, and then move P1 around the user coordinates. The y-axis of the system is rotated by 10 degrees, and the changed position is the result of the plane transformation. Kinematics inverse solution instruction. Calculate the input Cartesian space position according to the selected reference angular value and the joint space coordinates corresponding to each other in the same solution space. We manually enter the Cartesian space position in P1 and manually enter the joint space position in P2, which is a position of our reference point. The socket sends the result of the inverse solution. The parameters of the inverse solution are P variables. The reference point is P2. Lift the robot to the position P1 in a straight line. After the movement is in place, the socket sends the current joint angle value and the robot joint moves to the result position of the inverse solution. After the movement is in place, the socket sends the angle values of the current fixed joint angle of the robot. The following figures show a result received by the socket, and the result is the same 3 times. The meaning of the kinematic positive solution instruction is to calculate the position of the Cartesian space where the input joint angle is located. In the position variable P1 manually input the joint angle coordinates. The socket sends the result of the correct solution. Before the joint is moved to the position of P1, the socket sends the coordinate of the center position of the robot's end flange. The robot moves to the result of the positive solution in a linear motion. After the movement is in place, the socket sends the coordinate of the center position of the end flange of the robot. The following figures show the 3 results received by the socket. This is the end of this training. Thank you for your attention.